Right. Okay. So last week, what we have, learned and what we have explored are some of the very fundamental concepts in soil mechanics. So last week we talked about the physical and mechanical parameters of soil. We also discussed about the role of clay minerals. We also discussed about how to analyze particle size distributions using sieve analysis, and we compute all those numbers into the graph so that we can understand whether the gradation is poorly graded or whether it is well graded, and etc. Okay. Last week we also discussed about the shape of soil particles and how it affects the behavior of soil. So the concept that we discussed last week are so essential because they give us the, so-called basic language, to describe the soil as a material. To give you some of the analogy, so we can say that just like a doctor, before you can, give a verdict regarding your patient, you must know the anatomy, right? So having the knowledge of the anatomy, then you can have a robust diagnosis of what your patient actually are suffering. So in the context of civil engineering, as a civil engineers, we must know soil properties before we can design foundations, we can design embankment and so. So, these understanding are so crucial. So this week, what we are going to do is to connect these basic soil parameters into relationships that really help us understand the soil behavior in more quantitative way. So when it comes to soil mechanics, we're not only talking about the concept, right? So we're also talking about how these concepts are translated into numbers, how these numbers are going to be interpreted, then we can be sure or we can have a verdict regarding whether certain soils are going to behave certain way and how it means in terms of our design, whether the soil is safe for the constructions, whether this type of soil are suitable for certain types of foundations, etc. So the concept, the numbers are going to determine what kind of design we are going to propose for whatever context. Okay. So for this week, we will study about how parameters such as specific gravity, unit weight, water content, point ratio, and degree of saturation are related to each other. Okay. So I'm going to also introduce the concept of relative density, which is, particularly important for sandy soils. And at the end of this lecture, I'm going to also discuss about the soil grain size characteristics. Okay. So I'm going to also introduce the term like D50, okay, which indicates the soil performance, and all of those topics are going to be covered for this week and next week lectures. Okay, so I'm going to divide the materials, the slide presentation into two weeks of lectures. Okay, so for the first part, I'm going to focus on um, the parameters, okay, which is specific gravity, the degree of saturation, and how you should, perceive these parameters and numbers. Okay, right. So when it comes to this week's lecture, I'm going to give you some of the uh, explanation regarding why that you all need to understand about these parameters and why these are important in terms of the design. Okay, so when we are talking about soil mechanics and talking about those parameters that I have just mentioned before, this is so crucial, especially for geotechnical engineers. Okay, because as I mentioned before, when we design a foundation, so we need to know whether the soil will compress, okay, whether the soil will, the form will experience a settlement when we expose them with a loading or we expose them with a certain force, okay. So it is important, right? So because we don't want to construct something on soil that will compress drastically when we, put uh, some infrastructure above that. Okay. We would like to also know about how soil behaves in relation to water. Okay, so we would like to know whether the soil hold water, whether the soil will behave in a way that it's going to expand when they absorb water. Okay, we would like to also know about how dense the soil. Okay, so these considerations are very important when we are designing foundation. Okay, so when we build embankment or highway, relative density really help us check whether the compaction of a soil has reached the required standard or uh, required percentage of a compaction. Okay, so when it comes to also grain size distribution, so this parameter also important when it comes to the designing because it becomes the basis for us to classifying the soil. uh, when we know the grain size distribution, we can also predict the probability, how quick the water dissipate from soil, or how quick or how slow the water is going to be hold or is going to mobilize throughout the void of the soil. Okay, and ultimately, what this information tells you is about the stability and the strength of the soil. Okay, so in other words, I can say that the topics regarding the soil characteristics and the parameters in relation to the soil itself is going to really help you to bridge the understanding regarding uh, the soil data that you are going to collect from the experimentation at the lab, okay, or experimentation that you are undertaking at the site, which we usually call them in situ investigation, okay, and how you are going to understand these numbers. How does that mean in terms of the soil behavior, and how does that affect the practical aspect of your design, okay, in the field. So basically, what we are going to do this week is that we are going to linking the theory, the concept, into the practice. So how this number is going to mean in terms of the design. Okay. So basically, what we are going to focus for this week is about understanding the formula, understanding the principle behind that formula. Okay. So basically, it going to involve a lot of calculation, a lot of interpretation. So yeah, you really need to pay attention throughout this lecture so that you can really understand and you can accurately use the formula in accordance to the condition and in accordance to the design that you are required to undertake. Okay, so that's basically what is the objective of today's lecture. Okay, so yeah, for this week we are going to focus on the soil parameters relationship and also relative density. And for next week, we are going to focus more on the other parameters like E. E is the void ratio. I'm going to briefly explain that later in the end of the lecture so that you can make sense of this parameters and why this parameter is important. And lastly, in the third week, at the end of the week third, we are going to discuss about the parameter called D50. So that um, is related to the sizing parameters of the uh, gravel or granular soil. Okay. So without further ado, I think I'm just going to proceed with our topic today. So yeah, when it comes to the soil mechanics and talking about the soil. And if I'm not mistaken, I have discussed this in the first week, but if I haven't, then I think this is the right time to introduce you this concept. So in civil engineering, okay, so soil is one of the most important materials that we work with. Yeah. So just like concrete or just like steel, those are the major components of civil engineering infrastructure. But when it comes to soil, soil is more complicated, okay, because it is naturally formed and it is not manufactured. And what does that mean? That means that we need to understand how soil is structured and how it behaves under different conditions. Okay, so when it comes to soil, we we would call soil as a three-phase system. Okay, so what does three-phase system mean? Okay, so soil is not just solid particles. Okay, so if we take um, handful of soil, okay, so it has actually three components in the soil. So what are those three components? So first is the solid, okay, or the solid grains, and it also contains water, and it also contains air. Okay, so three-phase system means that uh, soil is comprised of three major components. Okay, solid, which is the soil particles or soil grains, water, and air. Okay, so that's why we call soil a three-phase system. Okay, so if there is no water in the soil, only air and solids, okay, we would call that soil as a dry soil. Okay, so if there's no water in it, if the voids are completely filled with water, okay, so there's no space for the air to be trapped inside the soil system or three-phase system. Okay, so that means that the soil is saturated. So that's why would uh, we would oftenly encounter term like saturated soil. Okay, so that means that the voids are completely filled with water. So there's no air being trapped, even inside the you know uh, uh, the, the 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 soil grains or even inside the water. Okay, so there's no air trapped. Okay. Uh, in the third scenario, if the soil has both air and water, then it means that the soil is a moist soil. Okay, so we have a term for the dry soil when there is no water in soil. There's a term for soil where the voids are completely filled with water, and that means that the soil is saturated or saturated soil. And if the soil contains both water and air and solid grains, it means we would call the soil sample as a moist soil. Okay, so to make it easier for you to imagine this, explanation, I want you to imagine a sponge. Okay, so when you let the sponge to absorb water, okay, so then it means that when they absorb the water, it's going to fill those, void inside the sponge, right, with water, right? So it means that, or what that can mean whether the sponge is wet partially or it is fully soaked. It depends on how much of water um, the sponge is, absorbing. Okay, so you can call it whether it is wet. It means that there are some void inside the sponge that is not filled with water, and there are some filled with water. But if it is fully soaked with water, it means that all the void inside the sponge is filled with water. It means that the sponge is fully saturated. Okay, and that also means that in the context of soil, that's also what happens. But when the sponge, yeah, when you squeeze the sponge, yeah, squeeze it until all the moisture inside the sponge is being, expelled out, right? So and it makes the sponge is completely dry. So that's how we can, equate that with a condition of dry soil, because there's no water left or trapped inside the soil. So that's why it is important for all of you to understand how this terminology and how it relates to the behavior of the soil itself. Okay, so as civil engineers or geotechnical engineers, then why this uh, concept is important? Okay, because when it comes to the amount of water and amount of air exist in soil, right? Yeah, those quantities, okay, on how much air and how much water is going to affect the behavior of soil. So in what aspect of soil it's going to affect? So it affects the strength of the soil. It affects the compressibility of the soil. Okay. It affects the stability of rock. Okay. So well, I'm going to explain this later in the next weeks in terms of how it affects the strength. But to give you a brief illustration of how it affects the strength. So, for example, when it comes to the strength, yeah. So when we don't have any water left inside the three-phase system, okay. So what we have left is only air and solid grain. Okay, the amount of friction that is going to be generated from the friction between solid to solid grains is going to be much higher in comparison to the friction that is caused by the contact between water and solid grains. Okay, because solid and solid, because they are both stiff. Okay, so it is much greater in terms of the friction generated. But when it comes to water, which is liquid, which is in terms of its stiffness, they are completely different with the solid grains. It means that the amount of friction generated are comparatively much weaker, right, in comparison to the solid-solid contact. Okay, so that's why when it comes to the soil behavior, when it comes to its strength, it's going to be comparatively weaker when you have more water and air in comparison to you have less of them. Okay, so that how I can explain about the strength. When it comes to compressibility, soil is going to be much more compressible, okay, or they are experiencing more deformation or settlement when it contains more water and air, okay, because air and water, they can easily be compressed or they can easily be squeezed out of the soil three-phase systems, or they can easily be mobilized through the application of loading. Okay, so when you have more air and more water inside the three-phase system of soil, then it's going to compress more, and you have to be worried about the soil that has the higher potential to compress. Because, for example, when you're building something, and when you build something and they are still compressing, they're still deforming, they're still moving downward, it means that the soil is going to affect the integrity and the safety of the infrastructure above it. So that's why strength and compressibility are those two uh, parameters, those two phenomena and those two parameters that you really want to look at and to ensure that we can have the soils that withstand any potential external exposure you're going to uh, give to the soil. Okay, meaning that you want the soil to withstand the potential loading or potential change of um, uh, volume due to this application of load. Okay, in which that it's going to really affect the overall stability of the soil. Okay, so that's why yeah, given the examples and explanation I gave you before, so that's why a saturated soil are a type of soil that we try to avoid, okay, because saturated soil may become weak and fail during the heavy rain or earthquake, okay. So heavy rain when the amount of moisture excessively exists uh, in the site abundantly, and that would definitely affect the three-phase system of the soil itself. Okay, so basically, um, understanding this information, so you can definitely understand how to describe soil in terms of the numbers. Okay, because we need to translate this the concept of saturation or the amount of water, the amount of air in terms of the numbers of the soil parameters. Okay, so Through this lecture, so what we are going to do is to understand and to develop a relationship between volume and weight of the soil. Okay, so through the lecture, I want you to have the understanding of how we can define point ratio, porosity, the degree of saturation, and you can tell us how much of space in the soil is being occupied by air or is occupied by water. Okay, I think that's very important. And also, I think it's important out of this lecture that you can define the relationship between moisture content and unit weights, and you can also having a good articulation of how heavy the soil and how the soil is how the the weight of the soil is depending on whether they are dry, they are moist, or they are saturated. Okay, so basically that's what we try to aim for out of this lecture. Okay, so moving on to the next slide, which we are going to focus more on the calculation and understanding this three-phase system. Okay, right. So I think it's quite clear from the slide that um, there are illustration, yeah, in terms of the three-phase system. So let's begin with what we see in the soil sample in the picture. Okay. So as I mentioned before, that soil is not just a solid grade. Okay. So it also has empty spaces between the grains. Okay. And these empty spaces or these spaces are called voids. Okay. Okay. Voids are, or in Indonesia we call it poros. Yeah. So there are voids in between the grains. And these voids can be filled with water, with air, or with both of them. Okay, yeah. So every soil sample can be thought of as having three parts. Okay, the solids, water, and air. Okay, so as I mentioned before, that it so in three-phase system, we need not to have uh, all these three elements for calling for calling a soil as a soil. Okay, so normally in a soil composition that we have three all these three elements. Otherwise, that we probably can have only two or probably only have one. Okay, and the primary element of the soil is definitely the soil particles. Okay, or the solids. Then the solids can behave differently when we have water, and it's going to be much more dynamic when we have air inside, being trapped inside this three-phase system. Okay. Now, first and foremost, what we would like to discuss first is about the basic formula regarding the volume of a given soil. Okay. So as you can see in the slide, that the total volume of soil, okay, which in this case we call them C or volume, made up of three major components. Okay, so the first component is definitely the volume of solids. Okay, second one is the volume of water. Okay, and we denote them as PW, the volume of solid. It's is denoted as TS or volume of solid, and also lastly is the volume of air. Okay, so mathematically we can write the formula for the volume of a given soil or a volume of a soil as C equals to TS plus PW and P A or volume of A. Okay, so this is basically just suggests that the total space taken up by soil is comprised of space of solids, space of water, and space of air. Okay, so I think this is quite straightforward. It's not hard to understand. Okay, so the next one that I think addresses the differences that we need to really understand. So volume doesn't equate to weights, and I think it's quite intuitive to assume this, okay? But especially in the context of soil, I think it is important for us to really, understand the difference, okay? So the next one that I'm going to explain is about the weight. Okay? So air has almost no weight, okay? So it doesn't carry any weight, okay? So for air, you can just ignore. But that means that what is left is that the total weight of soil sample, okay, or in this case, we call them W or weight, only comes from two elements, the weight of solids and the weight of water, okay? So, the formula can be represented as W equates to weight of solids and the weight of water, okay? And I think this is quite straightforward to be understood. Okay. Now, what you want to do next is to understand regarding the next relationship, which is the uh, E or point ratio. Okay. Now, when we are talking about point ratio, okay, as I mentioned before, that it relates to the amount of oil or porous. Okay, so point ratio actually tell us about how much empty space the soil has compared to the solid. Okay, so how much empty space, yeah, per the uh, the space being occupied by the solids. Okay, so to represent this mathematically, so we can write them as void ratio equates to the volume voids, okay, divided by or being compared with the volume of solids. Okay, so to reiterate one more, so the volume of void, okay, or PV is the volume of air and water, right? Okay, and volume as solids is the volume of the solid itself, so only the solid grains. Okay, so voids, yeah, is the volume that can be occupied by either air or water. Okay, now you should think of this like this. Okay, so if a soil has a high void ratio, and that necessarily means that there is a lot of empty space, yeah, relative to the solid particles. If it has high, yeah, void ratio, it means that there are more spaces that can be available to be occupied by water or air, okay, in comparison to the amount of space that is occupied by the solid particles itself or solid or the soil grains, okay? Now, um, what does that mean when it comes to the uh, situation where the void ratio is low? Now, it means that the particles are packed more tightly together, okay? And this means that the empty space is left that can be occupied or can be filled by uh, water and air. They are relatively much less in comparison to the solid, or in comparison to the space being occupied by the solid itself or the solid bit. Okay. Now, why this, number or the parameter is important? Because this will really help us to understand why some soil are strong and dense and why some soils are weak and they are compressible. Because the soil, if they are packed more tightly, yeah, leaving less space for air and water, they are associated with much stronger and dense soil. Okay. Now, if they have more spaces that can be exploited by water and voids, and that means, and that can easily be associated with soil that are more prone to compressibility, okay, and subsequently it means that the soil are much weaker. Okay, so that actually what and how we should approach this, parameters, and when we would be able to get the numbers, then and that's how we should approach the number. Okay, higher it means that they are stronger, lower it means sorry, yeah, if it has high point ratio, yeah, that's what is actually, sorry, if it has high point ratio, it means that the soil are most likely to be weak and compressible. If it has low high point ratio, it means that some soils are uh, associated with much better strength and much denser composition. Okay, that's what and how we should approach that. Okay, so I think it's clear. Okay. So yeah, for this slide, what I can summarize is that first, when it comes to the volume, so volume equation tells us how soil space is being divided into solids, water, and air. When it comes to weight, so the weight equation necessarily tell us that soil's weight comes only from solids and water because the weight of air is negligible. You can use more. Okay? They they don't carry any weight. So weight of air is most of the time have been excluded from the calculation. And lastly, when it comes to point ratio, it tells us how much empty space in soil in comparison to the solids in the soil that has occupied the space itself. Okay, so this basic relationship are the foundation for everything we do in soil mechanics, from calculating density to predicting settlement to estimating the strength of the soil. Yeah, we really need to understand and we really need to know uh, these parameters and how the numbers associated with this parameter means. Okay, so that's I think basically what I can tell for these three major equations related to weight relationship, weight volume relationship. Okay, right. Okay, so I think we are going to proceed to the next slide. If you have any question in pertaining to whatever I explained, if there is any terminology that you are not familiar with, just unmute your mic and feel free to just address the question. Okay, so we are going to just proceed. Right. So the next one is what we are going to discuss is about the porosity. Okay, porosity, saturation, moisture content, and humidity. So we are going to discuss that one by one. Right. So now that we know that soil is made of three major elements, solids, water, and air, so we need to describe how much space each part takes and how much weight it has. Okay, so the space and the weight. And to do that, I think as a civil engineer, we need to have uh, some complementary parameters that can really make our understanding better. Okay, so we are going to explain that one by one. So we get into the first one, which is the porosity, or it is denoted by N. Okay, so the formula for porosity is volume of voids divided by the total volume. Okay, so when it comes to porosity and what does it mean? So porosity is simply the fraction of the soil volume that is made up of empty spaces, okay, or voids. Okay, so I'm going to bring the sponge analogy again for for this explanation. Okay, so porosity in relation to the sponge, yeah. So porosity tells us how many holes are inside the sponge, yeah, compared to the total size of the sponge itself. Okay, so how many holes compared to the total size of or total dimension of the sponge. Okay, so a soil with high porosity, meaning that it has a lot of empty space between particles. Okay? A soil with low porosity, they are more tightly packed. It means that they don't have empty spaces between the particles. because they are being filled or they have been occupied by the solid itself. Okay, so that's how we explain about the porosity. Okay, so the fraction between the empty spaces. Okay, how many holes are in it inside the soil in comparison to the total size or total dimension of the soil itself. Okay, so uh, that is about the porosity. Second one is the degree of saturation, right? So degrees of saturation, the formula is volume of water is divided by volume of fluids. Okay. So what degree of saturation actually tells us? So degree of saturation is about how much of void space is filled with water. Okay. So how much of void space, the void, is being filled with water. Because I think it's important to reiterate again that voids can be filled by water and air. Okay, so the degree of saturation they indicate or they tells us so with the existing void spaces how much of these void spaces are being filled by water. Okay, so when it comes to the number, so degree of saturation they are always associated with the percentage. Okay, so we represent them in terms of the percentage. Okay, so let's say the saturation is zero, okay, or 0%. So if the degree of saturation is 0%, it means that the soil is completely dry, okay? Because if the saturation is zero, it means that there is no water occupying the existing void spaces, okay? Now, if the S or the saturation is 100%, that means that the soil is fully saturated. It means that all the voids existing are being filled by water, okay? And when it comes to uh, the context in the field, okay, so most natural soils, okay, they are somewhere in between, okay. Uh, that means that um, we can we can find the soil to be in a state of completely dry, so that's why we can call them a dry soil, or we can also find the soil to be in the state of fully saturated, okay. But we can also find them in a condition where they are in between. It means that there are some part of the void being filled with water and some part are being filled by air. Okay, so that's why it's quite common for us to encounter soils to have a degree of saturation and between of I don't know, be it from the 30 to 40% to as high as 70 to 80%. Okay. So that's what we commonly encounter when we are in the field. Okay. So degree saturation is about void spaces, okay, being filled by water. Okay. So it has nothing to do with the solids. Okay. It has anything to do with the void spaces and uh, uh, how much water occupies that void spaces. Okay, so that's what we do of saturation actually indicates. Now we are moving on to the next parameter. So the next parameter is going to be the void ratio, which I think I have uh, mentioned before. Okay, so there are two uh, extended iteration of this formula. So as you can see in the slide, that you can see that void ratio is not only related to the volume of voids in comparison to the volume of solids, but also it can be associated or it can be related to the porosity. Okay, so as you can see in the slide that uh, E or void ratio equates to porosity divided by 1 minus porosity. Okay, so earlier we get to understand that the void ratio, which is the ratio of voids to solids, okay, now porosity and void ratio, they are closely related as it is represented by the formula. So they both describe how much space in the soil has between particles, but in a slightly different ways. Okay, so so here's the thing. You don't need to memorize. You don't need to worry about memorizing this formula. But what you need to understand is that when it comes to void ratio and porosity, they are correlated. Okay, they are basically two sides of the same coin. Okay? So high porosity means high void ratio. Okay, so you can see that they are linearly related. Okay, low porosity means that they have low void ratio. Okay, so that's why to represent the void ratio or conversely porosity to a void ratio, it can be represented in the formula that as you can see in the slide. Okay, yeah. So that's basically what I'm trying to say is that void ratio and porosity they are linearly correlated. Now, moving on to the next one, which is the moisture content. And I think this one you really need to pay attention to the definition because I encounter so many civil engineers. They are twisting and mixing up the definition of moisture content, especially when you're talking about moisture content of soil. Okay, so when it comes to moisture content, so what they actually tell us, okay, so moisture content is basically related to how much water is in the soil compared to the weight of the solid particles. Okay, so water compared to the solid particles. Okay, so what kind of mix up and twisting that I usually encounter when it comes to the definition is that so some of the civil engineers, they can perceive moisture content, yeah, as uh, the amount of moisture in comparison to the weight of moisture. Sorry, sorry. So what usually the misunderstanding that I encounter is that they usually uh, count or they usually perceive that moisture content should be about the division between or the subtraction, not subtraction, the division between the moisture, so the weight of moisture divided by weight of water and weight of solids. But when it comes to the context of soil mechanics and counting or estimating the moisture content of soil, we should not take into account the weight of the water anymore. Okay, so just weight of the water uh, divided by the weight of solids. Okay, so for example, 100 grams of dry soil, it contains 20 gram of water. Okay, so the moisture content is 20%. Okay, so uh, we do not take into account like the so when it comes to the moisture content, so we try to separate, yeah, between the weights of the waters and the weights of the dry. So it's always about the weight of water and the weight of dry soil. So you cannot assume that uh, to to calculate or to estimate moisture content that you're going to take into account the weight of soil that also contains moisture. We should not. We should get rid of that inside your calculation. Okay? And I think it is also important to understand about the moisture content because the moisture content always associated with the soil strength and compressibility. Uh, the more moisture that the soil holds, then it means that the strength is weaker and the compressibility is higher. For this density formation approach and understand that. All right. So we are moving on to the unit weight or gamma. Okay. So unit weight of soil or gamma is the weight of soil per unit of volume. Okay. So in other words, this actually tells you how heavy the soil is compared to its size. Okay. So water and volume. Okay. So first and foremost, I think what you need to understand is that dry soil, they have they have essentially lower unit weight. Okay, and I think that's for a very good reason because uh, the dry soil they usually weight less, okay, and they occupy less spaces. Okay, so that's why dry soil usually has lower unit weight. Okay. Secondly, when it comes to saturated soil, comparatively, it has much higher unit weight, okay? Because we adding up the water, also adding up the void being occupied by uh, air, okay? So yeah, basically, not only they are occupying more space, okay, but they also add more weight, okay, because it contains water. So, here's the thing, it can um, it can contain more water, but when it comes to the volume, it doesn't change that much. Okay, so what aspect that really adding up to the unit weight of that soil for saturated soil is that the amount of water and the weight of water it carries. Okay, and I think this is critical when it comes to the civil engineering context because unit weight directly affects the load the loads soil can impose on structures, okay? Or in other words, it really affects the stability of slope. Okay, so the stability of slopes is highly contingent upon the unit weight of the soil. Okay, so that's why it's really important for you to understand. Okay, now what is left in this slide? Okay, the last one that I would like to explain in the slide is the relationship of the moist unit weight or the unit weight with moisture content. Okay, right. So, what we can see from the slide is that we can see how we try to correlate this parameter to each other, and we try to combine these parameters into a one complete integrated formula. Okay, so what the formula actually tells you. So when it comes to this formula, the total unit weight of soil depends, on the weight of solids plus water. Yeah, and I think uh, it really being presented in the formula. So that's why the formula always includes the term 1 plus moisture content, okay? Because when moisture content increases, the soil gets heavier, okay? So that's why it is important that the unit weight, yeah, always correlated to the moisture content. The unit weight, the unit weight will increase when the moisture content increases, right? Okay, and that necessarily means that it also increases the weight of solids. So that's why we try to multiply the weight of solids with the weight, weight of um, water, okay, and divide it by volume. Then you can get the unit weight of a solid because that's the unit they try to represent the ratio between, not the ratio, the amount of weight of soil per the volume that soil occupies. Okay, so yeah, from this slide, what I can really tell you guys is that number one, porosity and void ratio tells us about the space in the soil. Okay, degree of saturation tells us how much of the space is being filled with water. The next one is moisture content. They tell us about how much water is in the soil compared to the solids. Okay, again, solids, yeah, not the solids plus water. Okay, the water compared to solids. And the last one is unit weight. Tells us about the the heaviness of the soil itself. So how heavy the soil is. Okay, and this parameter give us the fingerprints of the soil. So they really help the engineers to classify the soil, to predict how it will behave in the roads, in the dams, in the buildings, in the slope, etc. Okay, so that's why this is really important for all of you to master the understanding or master the principle behind these equations. Okay, so I think that's all for the slide that I present at the moment. Now we are moving on to the next one. Okay. Now the next one is now we are going to encounter a new terminology, which is gamma D. Okay. Now I think it is quite intuitive to just tell that the small d after the gamma uh, represent the condition in which that the, the the level of dryness of the soil itself. Okay, so okay, I think it is important that when it comes to understanding the behavior of soil and how we classify them, so we cannot just say the soil is loose. Okay, we cannot just say that oh the soil is wet. Okay, so what we need is that the number. Okay, we need to how to say we need to have um we need to have sort of explanation that we or numbers that can help us understand the the actual condition of the soil and how we should perceive them when it comes to the design and how we correlate them with the design that we try to make. Okay, but then I think it is also important that it is not only about the moisture, but the level of moisture. And I also think that when it comes to the moisture, that we have to also consider when it doesn't contain any moisture. Okay, so that's why for this slide, I'm going to talk about the dry condition. Okay, and dry condition is very important because dry unit weight or gamma D is used as a reference to compare soils uh, with the other soils, okay, with a foreign moisture. And also, this is important in terms of designing the compaction in the flow, okay? And I'm going to tell you later in the next slide, okay? So let's get into the dry unit weight, okay? So when it comes to the dry unit weight, okay, so this is the weight of soil but only the solids. Okay, so the weight of soil, but only solids. Okay, divided by the total volume. Okay, so it ignores the water and definitely ignores the air. Okay, so we use this because water can come and go. Okay, as I mentioned before, that depending on the permeability or the how quick water can escape the solids or escape the voids, okay? So basically, water can come and go, okay? But the thing that stay constant is the solids, okay? So why it is important is because by knowing the dry unit weight, it gives us the stable reference point, okay? So we have the reference point for the soil, okay, when they don't contain water or they don't contain air, okay? Now, to give you a simple analogy regarding this dry unit weight, okay? So let's imagine two buckets of soil, okay? The one is dry, the other is moist. The moist one is definitely heavier, okay? But, it can contain the same solids as the other one, okay? Which is the dry one, okay? So, what is the difference is only the amount of water, okay? So definitely, the one that only contain solids, okay, we would definitely asking the question on how heavy the soil if it doesn't contain any water or when we dry them in the oil. Okay, so that's why I think drying weight is important because it gives you the understanding of the level of compaction. It gives you understanding of when the water doesn't exist, then how and what is the the level of compactions that this soil can experience. Okay, so to give you the illustration, so on the construction sites, when we compact soil for roads or for embankment, we compare the dry unit weight that we achieve in the sites to the maximum possible dry unit weight from lab test. Okay, so we have the reference point in the lab and we try to compare that with what we can potentially and possibly achieve in the site. Okay. Now, that really gives you understanding regarding the amount of control that we can have to the soil in relation to the compaction. Okay. So compaction means that we try to make the soil to be dense. We try to, you know, uh, uh, um, we try to expel the water out of the soil so that the soil can behave much more stronger. They can have much more uh, or better response to the loading, etc. So that's why I think it is important to understand this dry unit, okay, as the means to have a better understanding of the compaction that we undertake at the slide, at the sites. Okay, so that's why I think is crucial when it comes to the dry unit rate. Now, as you can see, the formula below the one that I just recently explained. So the formula 3.12, yeah. So it um it is represented with other parameters, okay, inside the formula. So as you can see there, that the formula shows how dry unit weight, moist unit weight, and moisture content are related. Okay, so how do you um, interpret this formula? So if moisture content increases, then the denominator becomes bigger. Okay, so the dry unit of the soil, okay, the dry unit weight, they would decrease. Okay, and the way that we should understand is that because more water makes the soil heavier, okay? But when we dry it, we are left with fewer solids per total volume, okay? So I'm not saying that the solids are going to be expelled, but I'm trying to say is that so for the soil, for the, for the soil samples, with, let's say two soil samples with typical characteristics, when you dry one of them, then they are going to weigh much less. Okay, although that one that you have dried and the one that you haven't dried, they have same weight of um, um, the solids. Okay, so basically, um, I'm just trying to say that the amount of water being expelled or the amount of uh, reduction of moisture content would definitely affect the number of or the value of the drying weight itself. Okay, so that's why in the field, okay, once we know the unit weight of soil in the moist condition or moist unit weight, and if you know the moisture content, then we can definitely calculate the uh, dry unit weight of that soil. Okay? And the number is definitely lower than the soil's unit weight in the moist condition. Okay, so that's what I'm trying to say. Yes. Okay. I think it's quite straightforward. No need to worry about the level of difficulties. We just need to understand and making sense of the explanation that I just provided, so that you understand that how you are going to strategically, use this formula inside your college. Okay. Now, moving on to the density and unit rates, and I think this is quite common, and I think you have been introduced to this formula when you are in the high school. Okay, so the next one is about density and unit rate, okay, and how they are correlated to each other. So instead of unit rates, sometimes we also talk about density, okay? So density means that uh, or what does it actually represent is the mass per volume. Okay, so the only difference with the dry unit weight is that the unit weight means or equates with weight per volume, and density equates to mass and volume. Okay, so what is the commonality here is that they are related by gravity, right? So gamma in here, we can compute them by uh, multiplying the gravity or the acceleration due to gravity, which is 9.81 or 10 meter per second quadrat, multiplied by the density divided by 1000. Okay, and that's how we are able to compute the gamma or the unit rate. Okay, so again, to make it easier for you to understand this, try to imagine about cooking rice. Okay, so if you weigh a cup of dry rice, okay, that's like the dry density. Okay, because it doesn't contain any moisture. It is just dry because probably you don't like this rice being exposed to the moisture, right? Okay. Then if you weigh this rice with water, okay, uh, and probably you would do this after cooking because to cook rice, then you need to add water, right? Now the rice is going to weigh heavier, okay, but the dry density hasn't changed. What changes is only the moisture, okay? So that's how you should understand this, okay? So that's how and that's how and what really changes in terms of the soil and in relation to the amount of water and the total weights that we can observe from this group of soil. Okay, so what I'm trying to say as well is that before we move on to the next slide is that as you can see in the table, okay, so what this table is actually showing you is that um, so here's the thing. When it comes to the soil, once we know the numbers, once we know the value of each parameters, now it becomes more practical for you when it comes to the design. Okay, so uh, so basically, when we have some typical values of the port ratio and the natural moist content, then we also get the drying rate for different soil. Okay, so then we can have the expected range for each soil classification. So as you can see on the table, so loose sand, they usually have high void ratio at the void ratio of 0.8, and the dry unit rate is usually quite low, in the range of 14.2.3 to 14.5 kilonewton per meter cube. Okay, so for dense sand, as I think I have mentioned before, that dense sand they usually have low void ratio. Okay, because they have more spaces in comparison to loose sand. Okay, sorry, the dense sand they have a low void ratio because they have less spaces being occupied. Okay, because they are being compacted probably, or the way that the particle being arranged, that it leaves less spaces in comparison to loose sand. Okay, and that necessarily means that because of the density, then it more likely to have higher drying rate. Okay, and I think comparing the granular to fine grain, and by fine grain I mean the clays, clays definitely has much higher void ratio, and that can the number can be double or triple in comparison to uh, granular soils, and the drying rates usually lower in comparison to sand and or any granular materials. Okay, so how you are going to use this table? So basically, this table this shows you the soil type and how it affects the density and strength. So dense soil can definitely support more load, okay? While loose soils or soft clays, they are much weaker, they are more compressible. So you really need to be wary of those type of soils. Okay, so you definitely need to undertake some degree of soil improvement, or I think you need to probably just change the soils So we just need to change the several centimeters or meters of this layer of soil, and we need to change the soils into something that is much more competent, much more stronger in terms of um, withstanding the potential loading that's going to be exposed. Okay, so that's I think what is important. Yeah, I think basically, yeah, when it comes to the understanding these numbers, I think it is related to convection, related to the preparation before we are constructing and anything above the soils, because we don't want the soils to compress, we don't want soils to deform, we don't want soils to suddenly um, dissipates so much moisture that uh, up to the point where it really challenge the integrity of the structure above. So I think that's what we really need to looking at. Okay, so I think yeah, that's it for this slide. Okay, so yeah, diluent weight, solids per volume, just ignore the water. It is related to moisture weight and moisture content, and you can just having a correlation that being represented in the formula, and then the density. It's just just another way for you to describe the ratio between mass and volume. Okay, and it really connects directly to the unit of weight. And when it comes to the typical values, as it has been included in the tables. It just helps you to understand different types of soils, how when it comes to denser soil and looser soils, and how we should approach them. Okay, so when it comes to the table, I think it is quite easy for us to imply that the sun and the sands or the granular materials, they are denser, they are stronger. Okay, and that means that we can rely more on the kind of type of soils. Okay? In terms of clays, they are softer, they are lighter, they contain more water, and that's I think what we really need to worry about. We really need to make sure that the clays they are competent, but by being competent means that the water should be expelled out so that we can rely on the weight and the strength that can be exerted from the solid grains of that place. Okay, that's what I can say. Right. So, I think, yeah, we are just going to move on to the next slide. Okay. Wait. Yeah. If you have any questions, feel free to just mute. Otherwise, I'm just going to move on. Yeah. Right. Okay. So, yeah. Right. So, yeah, the next one that what we are going to discuss is about um, the correlation among unit weight, weight ratio, moisture content, and specific gravity. I think we have to some extent covered that in the previous slides. Okay, so I think what I want you to look at first is the solid element once again. Okay, I think to make the calculation easier, I think we would assume that the volume of solid is just 1 unit. Okay, so the void space above the solids has a volume of E, E void ratio. Okay, so the total volume of the soil is 1 plus E. Okay, on the weight side, okay, when it comes to the weight, okay, the weight of solids is specific gravity multiplied by gamma W or weight of water. Okay, and when it comes to specific gravity, I think we have just covered that in the previous week. Okay, so specific gravity of soil. Okay, yeah. So for the weight of solids, so specific gravity of the soil, and the unit weight of water. And when it comes to weight of water, we can compute them by multiplying the moisture content multiplied by the weight of solids. Okay, or we can use other formula. We can multiply weight of uh, sorry, you can multiply specific gravity with moisture content and humidity of water. Okay, then one can get the weight. Right. Okay. So now the correlation between specific gravity with the weight and volume and unit weights of solid or water. Okay, so specific gravity is basically, as I also probably mentioned this in the previous week, is so basically specific gravity is a property of the solid particles. Okay, so it's just numbers that we use to represent the specific characteristics of the solid particles, which we perceive them as a property of the soil assets, yeah, in the three-phase system. Now, specific gravity, what they actually do is to compare how heavy soil particles in relation to water. Okay, so the soil particles compared to water. And for most soils, the range of specific gravity are in between 2.5 to 2.7. Okay, so what this actually tells you? So 2.6 and 2.7, it means that the soil solids are about 2.5 or 2.7 times heavier than water. Okay, so if have ever uh, encounter where we drop a stone in the water, it sinks right at the bottom of the 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 pool or wherever this water exists. Okay, so it definitely sinks at the bottom. Okay, now this is simply because the specific gravity of that stone is greater than one, which is one is the weight of water. Okay, so it means that the specific gravity of that stone is definitely much higher than the weight uh, of the water itself. Okay, so when I say that the soils is having the specific gravity in the range of 2.6 and 2.7, it means that the weight or the level of heaviness of the soil particles are 2.6 or 2.7 times higher in comparison to the water. Okay, so that's probably what I'm trying to say. Now, also in the last week, I mentioned about the relative buoyancy of that soil particles in comparison to the water, and I think that really um, affects the soil's behavior. Okay. Now, what is the next? Okay. The next one is the formula for unit weight of soil. Okay. So as you can see there, that the uh, formula for unit weight of solid is that weight of the solids and the divided by volume. Okay. Now, as you can see there, um, the numerator of that formula is the one is in the above, which is the 1 plus moisture content multiplied by specific gravity and unit of water. And that uh, the numerator that represents the total weight of the solids plus water, and the denominator, which is in the bottom, which is 1 plus E, or the point ratio, that represents the total volume of the solids and voids. Okay, um, so the total volume of the solids and the voids. Okay, so when it comes to the unit weight, they just simply indicate the weight over volume, which is when we are trying to represent them in the soil properties. So yeah, as you can see in the slide, that it is 1 plus moisture content multiplied by specific gravity multiplied by the liquid water divided by 1 plus void ratio. So what this formula really tells us, okay? So first one is that the void ratio increases, okay? So if the void ratio increases, it means soil is looser, then it means that the unit weight decreases. Okay, so the when void ratio increase, the unit weight decreases. Right, and I think that's can well you can really tell that from the structure of that formula because they are not positively linear; they are negatively linear when you see from the structure of the formula. Okay, so to reiterate again, so when the void ratio increases, definitely it will affect the unit weight in a way that it will decrease the unit weight. Second one is that if the water content increases, then it means that unit weight increases. Okay, now if solids are heavier, okay, so it means that if the solids are heavier, it means that the solids definitely or the soil has higher specific gravity, and that would contribute to the increase in unit weight. Okay, so unit weight will increase when the water content increases and the specific gravity increases. The only time unit weight decreases when the void ratio increases. Okay, so that's I think what and how we should approach that. Okay, what else? Okay, I think the one in the below. Okay, yeah, so dry unit weight. So for dry unit weight, that's the special case when there is no water, as I mentioned before. So you can notice that in the formula that it depends only on the solids and the fluid ratio. Okay, so if the soil is dense, in which that the E is definitely small, that's when the dry unit weight is high. Okay, that's what I can. Okay, um, okay, what's the next? E, yeah. Equates to specific gravity multiplied by unit weight of water divided by unit weight, the dry unit weight minus 1. Okay, so this one is a void ratio formula. So how we are going to use this formula? Okay, so if we know the dry unit weight and if we know the specific gravity of solids, then what we can do is that we can calculate the void ratio. And I think this is going to be really helpful uh, for us when we try to, we try to compute and try to estimate the void ratio because there's no need for us to move back and forth between the field measurement and soil properties. We just need to have the dry unit weights in specific gravity, then I think um, uh, we can just obtain this void ratio or through this calculation. Okay. I think I have also discussed about the degree of saturation, and this is just the other forms of formula that we can use to estimate the degree of saturation. Either you can use the equation 319, in which that shows that to calculate the degree of saturation, you can use the formula of multiplying moisture content with specific gravity divided by potential. So this formula, what they actually tells you is that degree of saturation is about how much of the voids are filled with water, and you can see that it is linked with moisture content, with ratio, and specific gravity. Okay, and I think that's yeah. I think we have already explained about how we should interpret the results of saturation testing. So basically, if it is 100%, it means that the soil is full saturated. Otherwise, that it means soil is not full saturated. It can be dry, it can be partially saturated. It depends on the percentage of the saturation. Okay, right. Yeah, I think we have only like 15 minutes left. I think I have 3 more slides to explain. Let's see. Okay. Mm, okay. How do I explain this? Okay. Yeah, just I think what I'm trying to say is that the other calculation or formula that we are going to see here is just the arrangement of some of the soil parameters and how they are going to be related uh, in the context of unit weight, the ratio, um, moisture content, specific gravity. So I think just need to get yourself familiar with this arrangement accordingly. So yeah. So what I'm trying to explain here is that as you can see here, the picture in the left hand side. So that represent the condition where the soil is fully saturated. So all the pore spaces are completely filled with water. So there's no air left inside the soil. And I think this is important because many soils in the field, especially the soils below the groundwater table. So the soils they are being saturated with the water due to the relative position of the groundwater table. So in that conditions, that soil are saturated. Okay. Now, when it comes to the calculation, I think what you need to understand and I think just another reiteration of what I have explained before that why so definitely you are wondering why there is one there, okay, and 1 plus E and etc. And I think I have explained this in the previous slide that we always assume that the voids have a volume equal to E, okay, uh, because the soil is fully saturated by both definitely those voids, but then the fill with water. So the way that we try to um, mm, interpret this, that the total volume definitely equals to 1 plus void ratio, okay? So that's I think how we should approach that. Okay. The next one, yeah, I think it's pretty much similar to the previous slide. So I think I'm not going to repeat again. It's just another way of arranging the formula so that we can calculate one of the parameters. Yeah. So I think, yeah, no need to probably memorize this. You just need to know the relative arrangement of each parameters to the other parameters in the formula. Okay, so yeah, probably uh, what I would suggest is just okay, probably just do more exercises so you can get yourself being familiar with this formula. Okay, that's probably what you can uh, suggest at the moment. Okay. What to say? Uh, oh yeah. Um. Uh. Equation 3.21. Yeah, I think it's important, yeah, for equation 3.21 on point ratio and specific gravity. Okay, so that equations actually connects point ratio, moisture content, and specific gravity. Okay, so if you know how much water the soil holds, and which that this is related to the moisture content, and we know the specific gravity, then we can definitely calculate the point ratio. Okay, yeah. Um, and sometimes when we know the ratio, then I think it really helps us in the soil classification because usually when the soil has high ratio, well, that means that the soil is loose. Okay, so they are more prone to they are more prone to compressibility. Okay, so when the E is lower, that means that the soil is much denser. It is much stronger in general. Okay. Okay, what else? Yeah, probably I'm just going to skip this one, the the explanation regarding the density relationship. Okay, yeah, just look at that. What else? This word as well. I think I have also explained about moisture content. Okay, then what else? Okay, mass of water. I guess the mass of water equates to moisture content multiplied by mass of solids. Okay, so basically, when it comes to the amount of water in soil, they heavily depends on the. Okay, firstly, the amount of water in soil. Yeah, it depends on how heavy the soil is. Okay, So how heavy the solid means that it is related to specific gravity. Second, the amount of water in soil depends on the density of the water. Okay, and it's that the rho W, okay, or rho of the water, or the density of the water. Okay, and lastly, it is related to the moisture content. Okay, so higher moisture content, it means that the amount of water is definitely higher. Okay, and in the context of civil engineering, if it contains more water, then it means that it is heavier. The soils are heavier. If the soil is heavier, it means that, for example, in designing the slope, okay, if the soil is heavier, it contains more water, then the potential failure of that slope is getting higher. Okay? Because adding more water, adding more weight, it means that it increases the driving forces for the stock to fail. So that's probably what I can say. Right. Okay. Um, okay. Okay. I probably this is another way to rearrange the formula, and basically they tells you the same thing, the relationship among unit of soil, porosity, and moisture content. Just need to get yourself familiar with the arrangement. Okay. What else? This one, I guess. Yeah, the same thing. Let's see so, right. Okay. So, yeah, we get into the last slide for this lecture. So, yeah, you can see here that I have included the example 3.2. Yeah, there's problems that I have included in the example, and there's also structured solution for the problem uh, of the uh, typical question example. So just yeah, firstly, I think just give it a try to solve that. Okay. Second, just compare your results with the results that I have included in the slide. Okay. Then I think yeah, it's going to be just fine. Right. I think I'm just going to stop uh, in terms of the material that I'm going to present for this week. Okay, because for the upcoming slide, it's going to be uh, for the next week. Okay. Now, uh, right. Okay. So, what I'm going to do is I'm going to take the academics of online lecturing for today. Uh, okay. Yeah. So before I wrap up this lecture, is there anyone who'd like to address any question? Okay. Yeah, but before that, I would like to just inform you that for next week, uh, hopefully we are going to carry this lecture in offline mode, and I'm just going to give you a earlier notice regarding the quizzes. So I'm going to take a great so I'm going to undertake uh, I'm going to conduct a quiz for next week. That's what I'm, yeah. So I'm going to do quiz for next week. So the topics that you need to prepare is the one that I explained for first week and second week. Okay. So the quiz is going to be about those two weeks. Okay. The questions is going to be in uh, multiple questions as so no multiple questions, multiple answers questions. Okay, so it's going to involve theoretical questions and some simple calculations questions. Okay, so you need to uh, make yourself be prepared for the quiz one. Okay, yeah. For the lecture materials.